start recording again, because that's good. Okay, so she's there on the surface. We know her weight is 800 newtons. Weight is Fg, yeah? Okay. So there's a couple ways we could do this. Nope, there's not. There's only one way we could do this. And then we're told that, or to figure out how much she would weigh, so if she was at an altitude equal to the radius. So we know it's the radius. So now we're going to take her and we're going to put her up here. Now this distance is what? If this was r, if the altitude is equal to the radius, we know that this is r and this is r. So this distance now from the center of the mass of the planet to the center of her is what? 2r. So we know that Fg equals gmm over r squared, and we know that this is equal to 800. What happens if instead I put 2r in the bottom here? Well, that's just going to be gmm over 2r all squared, which is going to be gmm over 4r squared once I solve that thing. Yeah, we see what we've done here? What I've done here? Now my question to you is this. What is this piece equal to? Gmm over r squared is gmm over r squared equals 800, yes? You see how I'm rationalizing that? So then this is going to equal 800 over 4, which is 200. So her mass is going to be 200 newtons. Which we did kind of talk about. If I double the radius, it's going to be 1/4 the mass. So no, not mass. 1/4 the weight. So this is a good problem. We should be able to understand how to do a problem like this. Does this problem help with the next problem? So let's talk this one through now, because I'm willing to bet if you couldn't do the first one, you probably couldn't do the second one. So a spaceship orbits a planet of radius r and weighs 10,000 newtons. How much would it weigh if it orbits a planet twice as massive as half the radius? Well, that's fun. We know that Fg, gmm over r squared, equals 10,000 newtons. And what we want to do now is we're going to put, how much would it weigh if it orbits a planet twice as massive. I'm assuming that's supposed to be and half the radius. I'm going to take a step here and suggest that that should be and. Just going to double check my key here. Wait for it. Yeah, this word here should be and. My bad. So what we're going to do is we're going to take big M and replace it with 2M. Thank you. Someone said that. Thank you, Jasmine. And we're going to take the radius and we're going to replace that with, we want half the radius. 1/2 r. We're going to put, instead of r, I'm going to put 0.5 r. Okay? So this is going to become g times 2m over m, or sorry, times little m, times 0.5 r in brackets squared. because we want a planet that's twice as massive. So I doubled the mass of the planet. And I halved the radius. And you got to be real careful here. It's not 0.5 r squared, it's 0.5 r all squared. Mathematically, it relates differently. So then we're going to shove this through here. So this is going to become, the 2 on the numerator is going to jump out front, GMM over. Now 0.5 squared is what?
1/4.
It's a quarter. So it's going to be 0.25 r squared. Now, what is 2 divided by 0.25? Because that's what we need, right? This piece here, we know what this is. What's this thing that I just circled? What's the value of that? It's 10,000. We were told that earlier. So now we just want to know what 2 divided by 0.25 is, and then we're going to multiply it by 10,000. It is 8. So 8 times 10,000 is 80,000. So 2 over 0.25, oh, no, we did that already. That's 8 times 10,000. So the weight of this spaceship in this new location is 80,000 newtons. The mass of the spaceship has not changed, but the weight has, because your weight's dependent on where you are. Okay, next one. Oh, weight, 80,000. Or did you want me to? That was a bad joke, I'm sorry. Okay. If you didn't get it, it was a really bad joke. Questions on this page? The answers are all at the bottom. The answers are actually in order. Nothing crazy there. I didn't take away the numbers that go in with the answers this time. Any questions about any of this? To number 3. Yes. If the gravitational force between objects of equal mass is 2.3 times 10 to the negative 8 newtons, when the objects are 10 meters apart, what is the mass of each object? Interesting. I feel like this question is designed to be tricky. So, number 3, here we go. Fg equals g mm over r squared. We are told the gravitational force between objects of equal mass is 2.3 times 10 to the negative 8 newtons. So, let's start filling this thing in here. Fg is going to be 2.3 times 10 to the negative 8 newtons when the objects are 10 meters apart. So now my r is going to be 10, and I have to square my r. Big G is always 6.67 times 10 to the negative 11. What do I do with big M and little m? What do I know about them? They're equal. No.
1 m times 2.
No. You're getting warmer. These two masses are the same, so I'm going to use the same variable for each. I'm just going to use little m for both, okay? So then m times m is what, Connor? Connor. Thank you, Jasmine. M squared, not 2m. So now I'm just going to take this value. I'm going to multiply by this, I'm going to divide by this, and square root. So it's not as tricky as I thought at first glance, because I misread the question. Do you want me to keep going, Angelina? Are you good? Okay. The trick there being that these two masses are the same, so I just write m squared there. Any other questions from the rest of those 11 questions? We were successful? Angelina? Number 10. I was just looking at number 10, wondering if anyone was going to ask me about number 10. Number 10. 3 objects, each with a mass of 10 kilos, are placed in a straight line 50 centimeters apart. What is the net gravitational force on the center object due to the other two? Nea's shaking her head. Like, you're unimpressed with this question? Were you unimpressed with this question?
No.
Oh, okay. You were just shaking your head after I finished reading it like you were unimpressed.
Was 0.
It is 0. Why is it 0? Can you explain why it's 0 before I do all the math?
Well, no, I saw net force, and then I saw the distances between them, and they were the same. So, and the masses are both the same.
So you deduced this without doing any math. So Angelina, that's a great way to approach this problem. Let's take a look at it. Net force being a key word there. Net force is the sum of all of the forces acting on our object, yeah? And we want to know what the sum of the forces on this middle guy is. So we know that there's going to be a gravitational force this way, and we know there's going to be a gravitational force this way. Are you cool with that? Okay. We know that Fg equals big G times mm over r squared. The masses, these two masses are the same. These two distances are the same. And this mass is going to be used in each question. And big G is the same. So if I have a force of gravity to the left, using all of those same variables, if I use that to calculate, or the values, sorry, if I use those same values to calculate Fg on the right, they're going to be equal, but they're going to be in opposite directions. So if I have two equal forces acting in opposite directions, F net has to be 0. 11 is the only one that requires you to actually do the math. But you'd approach it the same way. Fg equals gmm over r squared. The only difference here is that the mass on the right weighs 15 kilograms instead of 10. So it's going to be 5 times whatever the one on the left is, but that doesn't help us. We actually have to do it.
Number 7.
No, it's not going to be 5 times. What am I thinking? It'll be 1.5 times as big. Number 7. What is the gravitational force acting on a 70 kilogram object standing on Earth's surface? Why do you need me to do number 7?
I got confused because if you have a 0 on the denominator, then
You can have a 0 on the denominator.
exactly.
No, there is no 0 on the denominator.
Okay.
What's r?
I
What does it
thought
represent? The distance from what to what?
From the center of the 70 kilogram object to the center of.
There it is. You found your mistake?
Yes.
There it is. Which begs an interesting question. Well, how much would you weigh if you were at the center of the Earth? I'm asking you a question.
Oh,
How much would you weigh at the center of the Earth?
well,
Would your mass be infinite or 0? Because radius is 0.
well,
It would be definitely it's undefined.
what would it be?
Definitely, it's undefined. It's not. I have no idea. That's just an interesting little thought experiment.
So if we put something down.
Because all the mass is on the outside of you. So like the mass of the Earth would then be pulling you away from the center of the Earth, all equally in all directions. So I would say it would be 0.
Wouldn't it be down to like a very small point though, where it would be like
Let's just say your center was in the center of the Earth. You became one with the Earth.
Yes.
How did you say you go about for question 11? Because I got the answer, but I don't know if my work like.
Oh, I'm sure your work is fine. I was kind of thinking so you'd get an FG this way, and you'd get an FG this way. We'd plug in those values. The only thing that I said that was a little weird was I know that this FG is going to be 1.5 times this FG, but I don't actually know what that number is, so that knowing that doesn't help me.
So yeah, so I found. Yeah.
So you're going to have 6.67 times 10 times 10 divided by 0.5 squared. And on the right-hand side, you're going to have 6.67 times 10 to the negative 11 times 10 times 15 divided by 0.5 squared. One of those is positive, one's negative, so you add them together, and it's going to give you, I'm certain you did it correctly. Anybody else? We good? The reasoning makes sense. We understand these two. These two are great questions that may or may not show up at some point again in the future. We're happy with those? That style of question?
I need to like reward this question in the video.
Yeah, this is one that you're going to want to make sure you understand how to think your way through. If you know that FG, if you know a given value for FG, and then you manipulate the variables, the important thing to recognize is you might not know what these individual masses and radius are, but you know that combined, the weight is Fg, and that in this case is 800. So GMM over R squared is 800. And now when they tell you in the question how they manipulate those variables, if I double a mass, well it's instead of m, it's going to be 2m, and then the 2 comes out. So then it's going to be 2 times GMM over R squared. Oh, well that just means I double my previous weight. I know I said that rather quickly, but Luis, does that kind of thinking make sense?
Yeah.
Okay, that's how you approach all of this style of question. You always want to try and isolate for GMM over R squared and pull everything else out, like the manipulations to those variables out front, solve that for a constant, and then multiply it by the weight you were originally given. That's the technique for all of these. Okay. Flip the page. Let's do some more. We are going to look at gravitational field strength, and we're going to look at satellites today. Here we go. So, to explain how two bodies that are not in contact with each other can exert a force on each other, i.e. gravitational, magnetic, or electrostatic. We haven't talked about magnetic or electrostatic, but you guys have an understanding of magnetic fields, yes? Do we have an understanding of magnetic fields?
I think we do.
Has anyone ever used a compass?
Yes.
Compass only works because the Earth has a gigantic magnetic field around it, yeah? And so even though you can't necessarily feel it, it interacts on a really small level with magnetic objects. And so we can use the fact that there is a field, this magnetic field surrounding the Earth, protecting the Earth from crazy crap going out in space. We can use that. We can not manipulate it, but use it to perform a particular task. Yes?
The only thing that I know about it, like in chemistry, I read about it, like the molecules that have a positive and a negative side, and they can connect with each other.
Yeah, polarity, yeah. Yeah. So you're talking about polar molecules. That partial positive and a partial negative, they move around in relation to other partial positives and partial negatives. That is electrostatic force. So if you've taken chemistry and you've learned about polarity, that's exactly what you're talking about there. This one that we're going to talk about is we're going to talk about gravity. Now, a bunch of these forces that we've talked about are all one object directly connected to another one. I attach a rope to you and I give it a yank. There's going to be tension in the rope. You're going to feel the tension from the rope and it's going to pull you somewhere maybe. But with these three, gravitational, magnetic, and electrostatic, there isn't necessarily anything physically present, but there are properties of the space that interact with other objects, and we call those properties fields. So you're going to talk about magnetic and electrostatic in grade 12. This year we're going to talk about gravitational. So things with mass produce gravitational fields around them. If you went if the Earth and you were the only thing in the universe, and you went really, really, really far away from the Earth, we could say that you are in effect weightless. Yes? Because you're not interacting with the gravitational field. That's the thing that gives you weight. As you get closer to the Earth, your weight increases. Yes? Your mass doesn't change, but your weight is increasing because you're interacting more with the gravitational field. That's all of what we did down here. Just I didn't word it the same way. So, yes, Connor?
With your gravitational field, does it work in a spherical sense? So, like, if you were kind of...
Yes.
Okay, so...
Fields, Connor, are spheres of influence. They're invisible. They're intangible. They just demonstrate the strength of a particular characteristic at a certain distance, or actually, I don't like that certain distance. I'm going to say at a certain location within the field.
So, like with my hand, like potential force of gravity, would it be less than, like, if,
You're talking about the gravitational field that you yourself are emanating?
well, yes, because if I have a pencil sharpener,
Yep.
and let's say it's like way, way, way smaller to a scale that my actual force of gravity would be relevant to, would it be a lot less here at my hand because it's way farther away from my
Yes.
center? Yes. Okay.
That's just like if I mean the analogous example would be what happens if I take you and I put you in space.
I'm nothing.
You are well not nothing,
No,
not immediately.
I have mass.
If I put you on the space station, you're not weightless there. You would have a weight. Gravity is still acting on you. It gets weird because those objects aren't stationary. Those objects are actually moving. But they're not weightless. These fields that we're going to talk about here, I'm going to put a little asterisk here. We call these fields vector fields because all of these three kinds of fields that we talked about all have a directional impact. So like a gravitational field always interacts with you which way? Towards the center of the object creating the field. Doesn't matter where I put you around Earth, you're always going to be attracted to the center of the planet. Magnetic and electrostatic are a little bit more complicated. Gravitational interacts with your mass. Magnetic interacts with your anything about you that may be inherently magnetic. And electrical interacts with any part of you that is electrically charged. And the direction of these two is going to change. If you've ever played with magnets, you know that some magnets repel each other, some magnets attract each other. So a vector field that is a magnetic field can act in or out. Same with electrostatic. You can use charged objects to attract or repel each other. Sometimes the vector field is going to be out, sometimes the vector field is going to be in, dependent on the characteristics of the objects involved. We cool so far with this? Okay. The example that I give here is, you can think of like heat is also kind of a field. If you are around a what's it called? A campfire. The closer you get to the fire, the stronger the heat field becomes. The more you experience the heat of the fire. The further you get away, the cooler it is. And it doesn't matter which direction you are. If you're a meter to the side, or if I hang you a meter above the fire, you're going to experience it similarly. Actually, that's not entirely true. Never mind. Forget I said that. Heat rises, hot air rises. In a vacuum, you'd experience it equally. But it would be weird to think about what heat in a vacuum would feel like. But typically, let's think about it in a circle. This is a circular, not a spherical. As you get closer to the fire, the field becomes stronger. As you get, the stronger the field becomes. Likewise, the larger the fire, the stronger field. When we're dealing with gravitational fields, we define them. We already kind of have defined it already. We know the gravitational field strength, for example, at or near Earth. What is that number? It's 9.8. But we also called 9.8 what variable? Yeah, it's little g, right? So we've already done this. So let's do it up here. We've got Fg, gravitational field strength, is equal to m times, and I'm actually going to put the multiplication piece in there, m times little g. That's one way we had to calculate this. We also know, though, that this is going to be equal to gmm over r squared. So if we look at what's happening here, this was one way to figure out force of gravity. This is another way to figure out force of gravity. Both of them, though, involve this gravitational field strength term. In one of them, we call it little g. In the other one, we use this guy here, gm over r squared times the mass. Either way, the thing that I want you to see here is that our gravitational field strength, little g, this is grav field strength, is equal to, because these two expressions are equal, and I've got my mass term there and my mass term there, those two are equal. So little g itself then must be equal to gm over r squared. Big G times the mass of our object divided by the distance away from the center. So instead now of talking about the weight of an object around another object, we could say, what is the gravitational field strength at this location outside of this object? So instead of talking about Manuel and Connor and the attraction they have on each other, we can talk about just Manuel. What is the gravitational field strength at any point around Manuel? The units for this are going to be what?
The M is going to be like his like mass. R.
If you look at it right here, it's going to get kind of convoluted. Look at where it came from. Little g came from here. If I isolate this thing here for g, these units are, this unit right here is, look where I'm pointing, Connor. This unit is, so if I isolate for g here, it's going to be newtons over kilograms. It's a newton per kilogram. And that kind of makes sense, right? Like the force of gravity is dependent on, the force, N, is dependent on your mass. It's how much force is acting on a particular mass at a particular location. Alternatively, the units for little g, when we did it in the lab in the previous chapter, we called it an acceleration due to gravity. Accelerations are measured in meters per second squared. So our gravitational field strength can also be measured as an acceleration, because that's what it's going to do to an object. What is the acceleration caused by the gravity on an object at a particular location in space? This is how we calculate that. So let's do some examples. The Earth is not actually a perfect sphere. It's pretty close. If the Earth were, just to put it into perspective, if the Earth were the size of a bowling ball, it would be more spherical than the bowling ball is. That's how close the Earth is to being a perfect sphere. We cannot manufacture objects that are more spherical. But when you take an object like the Earth, you make it really big, we start to see the imperfections. And the weight, or the mass rather, of the Earth itself starts to warp it. So we get, well, sorry, it's not just it's the fact that that mass is spinning that warps it. Because it's spinning like a basketball, the middle kind of chubs out a little bit, and it actually makes this thing, our Earth is called an oblate spheroid. It's kind of pudgy in the middle. So what that does is it gives us different measurements for the radius of the Earth at different locations. For example, at the North Pole, the radius of the Earth is 6.37 times 10 to the 6 meters. At the equator, it's 6.386 times 10 to the 6. So, what is the acceleration due to gravity at those two locations? We have said up to this point that everywhere on the surface of the Earth, gravity is equal to 9.8 or 9.81 meters per second squared. That's the value we've used. But we can actually go and see how true that is. Let's do it. So I want to figure out the acceleration due to gravity. That is another way of asking for gravitational field strength. So I want to know what little g is at the North Pole. Little g is going to be big G times the mass of the Earth divided by the radius, how far away we are from that location. So big G is 6.67 times 10 to the negative 11. The mass of the Earth doesn't change. That value is, thank you, thank you. And now our radius is going to be this new radius, 6.37 times 10 to the 6 meters, and I want to make sure we square that. If you ran that through your calculator, what are you going to get? It shouldn't have that times 10 to the piece. It should just be 9.83. Newtons per. So slightly larger than the value that we've been using. Well, what about at the equator? Let's do it again. .98 times 10 to the 24, and now the radius that we're going to use is 6.386 times 10 to the 6. I want to make sure we squared that. So what is gravitational field strength at the equator? Anybody verify? Okay. So gravity's actually pulling you down a little bit slower at the equator than it is at the North Pole, because you're further away from the center of mass of the object. Practically speaking, does that really change anything? Not really. You're playing basketball and you shoot a basketball, like you shoot a free throw, you're not going to notice the ball coming down slightly slower. It will, but you'd never notice it. Mostly because everything else going on at the North Pole when you're playing basketball is going to be a huge distraction. One more example. We're cool with this one? Okay. The moon is 385,000 kilometers away from the Earth's surface. What's the gravitational field strength of the Earth at the moon? Well, G equals gm over r squared. So 6.67 times 10 to the negative 11. It's the Earth that we're concerned about. We want to know what the Earth's gravitational field strength is. So the mass of the Earth is 5.98 times 10 to the 24. What's the distance we're putting in for r? For gravity, well, first we're going to have to make sure it's in meters.
Yeah, that's what I did, 385 million.
But it's 385 million meters from what?
The center of the Earth.
That's not what the question says.
From the Earth's surface.
From the Earth's surface. So what do we have to include? We have to add to it the Earth's radius. So we want the first thing you did, Connor, was absolutely correct. We want to make sure this thing is in meters. There's going to be 385 million meters. So we want that 385 million. But we want to make sure we add to it the radius of the Earth, which is 6,380,000. Moon's really far away, it would appear. That doesn't change my statement. What's little g? Maybe I should calculate this one too. 6.67 e negative 11. 24 divided by 385 plus 6. What we got?
0.0026.
Absolutely. So if you were on the moon, is the Earth's gravity still acting on you? Yeah, it's acting. The Earth's gravity is acting on the moon, so the Earth's gravity better also be acting on you if you're on the moon. But would this be noticeable relative to the strength of the moon's gravitational pull on you? No. We've already calculated that value. Does anyone remember what the gravitational field strength of the moon is on its surface? Yeah, it was 1.6. Is that on the formula sheet, or did you remember that? It's on the formula sheet? No, where's my formula sheet? That's right beside me. G on the moon, 1.67 meters per second squared. The gravitational field strength of the Earth's gravity while you're on the moon, 0.0026. So the moon's gravity is 500 times stronger when you're on the surface of the moon than the gravitational field strength of the Earth. So yeah, you're never going to notice it. Yeah?
There is a way of those two gravities, like, some with each other, like, if you're on a specific spot, the gravity of the Earth and the moon.
Yes, well, that would mean that there is a spot in space between the Earth and the moon where the net force on you would be 0. Yes, there is a spot where you would just hang there between the Earth and the moon. Absolutely. That spot exists. Yep. It is interesting. I'm glad you picked up on that. That'll be part of what you do in Physics 12. But we could find it, but yes, that's a thing. Okay, the last piece here is we're going to talk about satellites here briefly. This is the beginnings of Physics 12. Yeah, you betcha. Okay, so this is the beginnings of a unit in Physics 12 called circular motion. So, given that the Earth and the Moon, the value that we're going to use here is 3.85 times 10 to the 8 meters apart, and that the mass of the Earth is this, and the mass of the Moon is this, we want to calculate the force of gravity between those two objects. So let's do it. Fg equals big G, big M, little m over r squared. So G is going to be 6.67 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24. The mass of the moon is 7.36 times 10 to the 22. And the distance between them, we're just going to use that value of 3.85 times 10 to the 8 meters. So 385 million meters. I want to make sure we square that. What's the force of gravity between those two objects? Yes, sir. Oh, did I put that in wrong? Oh, my bad. That was a typo. Thank you. What is FG?
You are also off by one on the radius. I'll flip it around a bit.
Did I screw that one up too?
It's 324.
Thank you. What's FG? 1.988. There it is. Times 10 to the what? 20 or 28? I got 20. No, double check. Double check.
I got 20.
Okay. So now we've established that there was a mistake in there. 1.988 times 10 to the 20 newtons. That is a massive number. The force of attraction between the Earth and the Moon is huge. Why does the Moon not simply slam into the Earth?
Because it's also attracted to the sun.
Because this force
No.
is in a direction that is not like slightly to the center like this. I think that this is represented as like the vector of this force is not actually pointing down. It's in a direction that it goes straight to.
No, this is gravity. This is a center seeking attractive force between the Earth and the Moon. The center of the Earth and the center of the Moon are attracted to each other with this strength. Why have they not slammed into each other already? Yeah. No, this FG, remember, Newton's third law, every action is equal to an opposite reaction. If the Moon is pulling, or if the Earth is pulling this hard on the Moon is also pulling this hard on the Earth. The question is, why do they not slam into each other? Sorry? No. If the Moon were static in space, it would slam into the Earth's surface. I'll tell you that much. So what is it about the Moon that is preventing it from doing that? Its orbit. Orbit implies what? It's moving which way? Around. So what we've got here is we've got the Earth, we've got the Moon. At some point in the Earth's past, the Moon was just a hunk of rock flying by Earth. Going that way. With some velocity v. As it got close enough to our Earth, it started to interact with the gravitational field strength of the Earth and got trapped in our, or in the Earth's gravitational field.
So the vector of these two directions is diagonal, so it's always diagonal.
Got to be careful with there's got to be careful with the vectors because we're adding, there's forces there and there's a velocity there. You're right, those are both vectors. It's this inward force here that prevents the Moon from going, but it's the velocity that the Moon has that prevents it from actually hitting the Earth. So what we've got here is we've got a Moon that's always trying to travel out as gravity is always trying to pull it in. So everywhere along this circle, or this path rather, because it's not a perfect circle, the Moon is trying to get away.
Wait, so then
And if at any point, if the Earth just ceased to exist, like Thanos snaps, Earth is gone. Not everyone is dead, but the Earth itself is gone. The Moon would just continue in a straight line from wherever it was on our orbit. Yes, sir.
if like a really, really big meteor came by, bigger than the Moon, and it came within a close enough distance to the Moon, then would the Moon change its trajectory and possibly out of its normal orbit range?
It would have to be pretty massive because the Earth is also pretty massive.
Just
Like that would also alter the Earth's orbit. Like there's a whole lot that would go on in that particular example. But theoretically, yes.
Would that?
Almost certainly. Okay, so let's talk about this same effect on a smaller level. If I throw a football like straight, what's football's going to do? If I throw it pretty weak, it's just going to go, right? If actually, I should go all the way to the ground. That should be kind of. Okay, if I throw a little stronger, what's it going to do? If I throw a little stronger, what's it going to do? Right? We're going to extend this now. Now, let's imagine instead of you throwing a football horizontally, you are now in charge of a cannon. Now, the cannon, we're going to contrive a ridiculous scenario here. The cannon is on top of a very high mountain, and we're able to ignore air friction somehow. You're going to shoot the cannon. If you shoot the cannon, the same thing is going to happen. The gravity is still going to act downwards, but because you're really high up, it's going to be able to go further because there's further to fall, right? So you've got like, maybe that happens. Yeah, you're starting to go around the Earth a little ways. Like we're talking like World War II artillery style here a little bit. What if I shoot it even further? Or even faster, rather? What if I shoot it even faster? So fast that as it tries to fall, it misses. What do we have now? Now we've got an orbit. So what is an orbit if it's not an object just trying to fall at the Earth and moving so fast it's constantly missing? That's all an orbit is. Objects in orbit are trying to fall to the surface of our planet. They're just moving so fast, they're constantly missing. It'd be frustrating if you were trying to get to the surface of Earth. Yeah? 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 Could we? Yeah. And in fact, we do to a certain degree. Like, there's lots of small objects that are orbiting our Earth, like the moon does, at varying distances between here and the moon. There's lots of satellites, millions of them.
Millions of satellites?
By definition, yes. Because all that space junk is technically a satellite, yeah? Yeah, actually it would. So now the physics of all of this get really, really quite complicated. Because if you want to actually hit the Earth, you have to be going at it, like you say, Tenjo, the right angle or the right speed. There's all sorts of factors now that determine whether or not an object's going to slam into the surface of the Earth or if it's going to continue in some sort of stable orbit.
And because space is frictionless, that moves.
Because space is a vacuum, it's not frictionless. There are other things that will interact with these things. The moon's gravity, you already said the sun's gravity. Jupiter's gravity, for example, is so massive that it actually causes a lot of these things flying through space to enter it instead of any planet in the inner system. Like that we see, the meteorites we see is actually pretty remarkable because Jupiter acts like a big cosmic vacuum going around our solar system, just sucking in everything that isn't more attracted to the sun. So this is an orbit. This is how this happens. This guy right here has just the right speed. To constantly miss Earth. i.e., it's in orbit. It's trying to fall. It's just failing miserably.
Wait, so could you do that like with the, well, I guess you couldn't because but like if you had a bullet that was right at the right spot, well.
Yeah.
If you had it going to the right velocity. So
If you were able to get it up to the right speed, absolutely. I mean, it doesn't have to be a bullet; it can be any object. But yes, if you get a large enough cannon, we could put someone in it, a person in orbit. That way, it's possible. The amount of energy you need is incredible, which is why we use rockets instead of cannons, because it's a constant stream of energy, so you need less of it. Or it's a constant stream of fuel, rather, so you need less of it. Okay, let's talk about this last piece here. Notice that at every point in orbit, the only force acting is what? Gravity. Always pulling in. Let's get rid of this. I don't want to talk about that last piece. And so you feel weightless because you're constantly in a state of free fall. You don't feel the effect of gravity on your mass. And that's it. I want you to, some homework I want you to do. There's 8 questions here, and you got 15 minutes left in class. Take a look. Do I want you to do this as well? There's another applet I want you to play with. If we had more time, I'd get you to do this. We'll start class with that tomorrow. Here we go. This is your homework. This is what I want you to do. You may use the washroom on your market take. Yeah, there's not a lot here. Should be okay.
Mr. Buda?
Yes, sir.
Are we still going to watch Gravity of the